here we go. All right, 13F. Most of it is pretty straightforward. There is a formula called the change of base formula that I think most students forget. But if you understand it in the way I'm teaching logarithms, you'll be able to derive it yourself and not need to memorize this rule. I guess the rule is nice to have though. But here we go. Let's begin with something like this. So remember how I said the only way for us so far to solve for x is we use solving by recognition or solving by inspection, right? That requires that what's on the left side and what's on the right side has to look exactly the same for you to do a comparison. This example here, it's not possible. 2 to the x, t equal to 7. You can't change that base 7 to a base 2, so you get stuck. So here's an example where you have to use inverse operations to solve. So here we are starting off with 2 to the x is equal to 7. What I want is this x. What I don't want is the base 2. Remember, that's the operation. Okay, so the operation is the positioning, and then the value is 2. We know so far that the opposite of exponential is log. Okay, so log is the operation. So here I do whatever you do to the left, so log. But since that's a base 2 exponential, then it's log base 2 exponential. Okay, so you can see that log base 2 is the operation, that's the value, and that was the exponential, and that's base 2. So whatever you do to the left, I now do to the right as well. So to the right, log 2 of 2. Based on this line here, essentially what I'm saying is I'm asking you to do log 2 of 2 to the x on the left, and I'm saying do log 2 of 7 on the right. What's convenient is these two are going to cancel out. They're inverse operations. Log base 2 of exponential base 2 will cancel out. And that's how you get x is equal to log 2 of 7. Okay, this is called the exact value. That's the exact value. If they wanted decimals, you type that in the calculator. Back in the past, you'd actually have to use a chart. You just go through the chart to find it. But that's log 2 of 7. That's the answer for the power. So 2 to the power of what will give you 7? 2 to the power of log 2 of 7. And whatever log 2 of 7 is, that is the power that you need. Okay? So you can see that I'm just doing inverse operations there. So this is what the line looks like. Log 2 of 2. Yeah? Let's do the same for the next one. This is a base 3. And technically, I'm going to do it a different way now. Okay, I'm going to do it a different way. You have 3 to the power of x minus 1 is equal to 10, right? Now, technically, if I ask you what's the inverse, you would still say it's log. So I'm going to do log again. And I would say log what? And you're saying, well, the quantity is 3. So you normally say base 3, right? So you say log base 3 and then log base 3 on both sides. What I'm trying to tell you now is that you don't actually have to. You can actually times whatever value. You can divide whatever value. Then that means you can log whatever base value. Yeah, it doesn't change the equation. So here, I'm going to get you to do on your calculator. Notice that there's 2 types of logs. One says ln and one says log. On your scientific calculator, they have the same 2 symbols, and both of them mean 2 different things. One means log base e. That's what ln means, log of a natural number. That's what ln stands for, which is log base e. And when they have log on your scientific calculator, it actually means log base 10. And the reason why is because in the past, with all the charts and when they used to use it manually, base 10 is what they had because we work in a decimal system, meaning 10-digit system. And they do have the values for log in a chart. And they also had exponential Euler's number. They also had it in a chart. So we referred to these two in a logbook to manually do it. I happened to be at the time where I didn't have to use the logbook, but I did know about it. My teachers used the logbook. Yeah. So you guys, by this point, we're all using our calculators to actually work out log base e and log base 10. That's why your scientific calculators can only do one of these two. What they can't do is what your CAS calculators can do, is they can't do that. So your scientific calculators can't do this. You can't actually type log base 2 of 7. So back in my time, how did I do it? Because we didn't have a CAS calculator to do what you guys are doing there. We had to only use log E and log 10. So in the mathematics, when we get to this point, we say, oh, well, the only 2 logs that I currently have in my logbook at the time, so I have to then use either log E or log 10. It doesn't actually matter. The point is, whatever you do to one side, you do to the other. So here, I can actually do log base 10 on the left. So log base 10 of whatever's on the left. Then whatever I do to the left, I do to the right. So here I would do log base 10 on the right. So why do we do this? So once we do this, this now gives me log 10 of 3 to the x minus 1 is equal to log 10 of 10, right? Unfortunately, these do not cancel out, okay, because they're not the same bases, so you can't just cross off the log 10 and the 3, but there is something we can do that you learnt in the previous exercise. We're trying to find x minus 1. We can isolate this by using one of the rules. Which rule do we use again? One of the rules can isolate that power. That's rule number 3, but you're correct. Rule number 3 says you can write the power at the front. So you can write it as x minus 1 times log base 10 of 3 is equal to log base 10 of 10. See, from this step, now, since that's a times log 10 of 3, that's a constant value. It doesn't have a variable anymore, that's a number. So now I can actually divide both sides to get rid of that times log 10 of 3. I can divide both sides by log 10 of 3. Log 10 of 3 divided by log 10 of 3 will be 1, because whatever that value is dividing itself. So that gives me now this equation. I end up with x minus 1. So that x minus 1 is left over on the left-hand side is equal to log 10 of 10 divided by log 10 of 3. We can solve for x now by adding 1 on both sides. Therefore, x is equal to log 10 of 10 over log 10 of 3 plus 1. That is exactly the same answer. If I did on my scientific calculator, it will be equivalent to you doing, had we done log base 3 on both sides, it would have been x equals to log base 3 of 10 plus 1. This on a CAS calculator will equal to that on a scientific calculator. Okay? Questions? You look confused? No? Good? All right. Now, this step here, see, notice how I went from here and I had to do a bit of rearrangement to get here. All right, so this step right there, this is called a change of base formula. What I'm going to show you underneath is the formula that you don't have to do log 10, you could do log E, you could do log 5, but the pattern will always be the same. See, if it was log 5, then I still can't cancel out this step. I still bring the power down, and the difference is that on both sides, it'll be log 5 of 10, log 5 of 3, and then over here, it'd still be log 5 of 10 divided by log 5 of 3 plus 1. So watch on the CAS calculator. I'm going to show you, even if I change this base, the answer is going to be the same for all of them. So watch this. You can get your CAS out too if you want to try it too. But check this out. I'm going to type in exactly what we just got there, and the answer is the same for all of them. So here we go. So on your CAS calculator, you are able to do log base 3 of 10 plus 1. This is what the x value should equal to. So that's what the power should be, right? What we've done so far is we did log 10 of 10 over log 10 of 3, and we said plus 1, right? Same answer, right? So this is on your scientific calculator where I said that we couldn't do base 3 Scientific calculators can't do that. So in the past we couldn't do that. We had to only do log 10, log 10. So I showed you the algebra how I got to this step, right? Now watch when I change it. It doesn't have to be 10. Could have been 5. Whoops. Let's do it again. Can you see the answer? All 3 of them are exactly the same. This is called a change of base formula because technically back in the past, we couldn't do these 2. So we could only do log 10 or log e, and that's what the formula is coming. So where's the steps? How do we see the changes? And if you look at the steps, it was here. At this point, when I said 3 to the x minus 1 equals 10, what did I do? I said log base 10 on the left, log base 10 on the right, but I didn't have to do log base 10. I could do log or whatever number I want, okay? And rule number 3 says you can bring the power down. So when you bring the power down, it doesn't matter what that base is. That could have been any number that you come up with. When you bring the power down, you still divide both sides. You'll end up with this fraction. And that fraction doesn't matter what that number is. That base could have been any number. Okay? So that's what I tried to prove down here. If that's what I'm trying to say here. A to the power of x equals y. And you can technically find that power by simply doing the log of any base you want. So here you could do log base 7 on the left, and you do log base 7 on the right. Then all it means is when you bring the power down using rule number 3, you'll end up with x is equal to, x times log 7 of a to the x is equal to log 7 of y. And same thing. See, to get x, you have to divide this over here. That's why it ends up being log whatever number you choose of y divided by log whatever number you choose of a. Because in this step here, all you're doing is you're just dividing by that log whatever number you chose. Do you see that? So I just chose 7 out of random, but it didn't have to be 7. It could have been any number, and that's why I wrote here whatever. So that could have been 10, could have been 10, could have been whatever the number you want. This is always going to cancel out. And then you end up with x is equal to that step. So this is what I'm saying. You don't have to memorize the formula. You can actually, if you understand the algebra to it, that's called a change of base formula. It's nice to know because one of the exams, I think back in 2020, I think it was the last question. It was a multiple choice question, and I think only about 7% of students who got it right. It was just this formula. There's just not many people know how to do it by hand now because you guys use a calculator all the time. Back then we couldn't, so we had to learn this as part of our techniques. Okay? All right, so let's now do a bit of practice so you get some ideas. So today is about using logs to solve the problem. So here we go. Let's solve for 0.2 to the power of x is equal to 0.6. Method 1. You can do it this way, the way I've been teaching it. Opposite of exponential is logarithms. So we say log, and we do log. The base, well, since it's a 0.2 base, you can do log 0.2 on the left, log 0.2 on the right. Log of 0.2 will cancel out. And if you have a CAS calculator, you can literally just type in log 0.2 of 0.6. Let's see what this equals to. So I'm going to type in cancel this out. Here we go. Log, control, log, 0.2 of 0.6. I get 0.317, roughly. 0.31739. Okay? Method number 2. Same thing. You got 0.2 to the power of x is equal to 0.6. You don't have to do log base 0.2. You can still do again log on both left and right, but you don't have to do the base of 0.2. It could be any number. So if you don't have a CAS calculator, you can do base 10 or base e. So I'll do base 10 just because we're used to the number 10. So log base 10, So here's the problem. These two can't cancel out. They're not the same bases. But I can use rule number 3, bring down the power. So rule number 3 of logs, we can bring the power down. So that means now it's x multiplied 2 log 10 of 0.2 is equal to the log 10 of 0.6. To get x, divide both sides by log 10 of 0.2. And so therefore I get x is equal to log 10 of 0.6 divided by log 10 of 0.2. Again, you can use the formula to memorize that. So you know that it's always this divided by the 0.2. Yeah, so you can just do x equals log e of 0.6 over log e of 0.2. But the pattern is that whatever's on the right will stay on the numerator, whatever's on the left, or the one with the power, will always have or be in the denominator. Okay, but the answer should be the same. So if you type that in your CAS now, if you did control enter log base 10 of 0.6 over log base 10 of 0.2, same answer. Okay, so on a scientific calculator, same answer, and on a CAS calculator, same answer. So that's method 1, method 2, called a change of base formula. Yeah.
Different change of base in the exercise 13E.
Yeah.
I had like log 10 bracket 10x over 3, and then I just raised it equals to 2. I raised it to 10 on both sides to get rid of the log 10, and it's 10 to the power of 2.
Yeah, that works.
How does that work?
No, but yours is different because yours started out with a log problem. I'm starting with an exponential problem. So that's why, so you cancel out the log by doing the opposite of log, which is exponential. I'm cancelling out the exponential by doing log.
Okay. So I was just wondering how that works.
Yeah.
Just start, I was looking at answers today, I figured out let's raise it to the power of 10.
Yeah, it's the opposite of whatever the base is. All right, team, let's do another example. Here we go. So that last one for that empty spot, you can pretty much do log of any number you want. So you can do log of 99.6. Thank you. Shh. That's an example. You could do log 99 of 0.6 divided by log 99 of 0.2, and it would still all be the same answers. Okay? Now, turn over the next page. This one you can have a go yourself. This is mainly for the next exercise. Once you start sketching, you'll realize why you've been practicing the algebra. It's to solve for x and y intercepts of exponentials. But let's do this one. Actually, yeah. So this is a mix of exponential and logs here. Notice that you've got 5 to the 2x and you've got 5 to the x here. This should be a hint. This is one of the examples I did in class last session about quadratics. So you have to turn into a quadratic problem. Notice that that's 5 to the x. You can rewrite this as 5 to the x all squared. So that changes the problem now, that you can say, let a equal to 5 to the x. This now becomes a squared minus 4 times a minus 5 equals 0. You see what I've done? All I did was I just replaced that with an a, that with an a. Okay, so 5 to the 2x just means 2 times x. But 5 to the power of x all squared, using rule number 3, you times those two together. So x times 2 or 2 times x means the same thing. The benefit of writing like this, if you replace 5 to the x with a, it becomes a squared, and that's an a. So it will be minus 4a minus 5, so that's what I got here. Then we factorize it. Chapter 3. Let's see if you can remember how to factorize. Who wants to have a go? What's factorizing this monic? I'm teaching my year 9s this at the moment. Factorizing. Christina. A minus 5. and A. All right. Very good. That is correct. A minus 5 times A plus 1. So you should get, therefore, using null factor law, A equals 5 or A equals 1. Negative 1. Thank you. So, replacing A again, that means 5 to the x could equal to 5 or 5 to the x can equal to negative 1. I just realized that I should have made it so the answer doesn't come out to 5 actually. Now you don't have to use logarithms to solve it. But anyways, this one, since we can use by inspection, both of them have a base 5, so clearly x equals 1 on the left-hand side. What about the right-hand side? It's impossible. 5 to the x, or every exponential, can never be negative. It's always a positive value. All right, so if you think about the graph as well, there's an asymptote at y equals 0. How is it possible that you're going to have a y equals a negative number? The graph doesn't even go into the negative region. Okay, so negative region is down here. X negative y equals negative 1 is down here. So it doesn't matter what x value you put in, you'll never get it. So hence this is undefined because 5 to the x is always greater than 0. Okay, so no answers for this one. So therefore there's only one answer. X has to equal to 1. Okay, for it to work. Why is this all this exponentials? Maybe there is a log part. Let's do this one. I'm pretty sure it's meant to end up being a log. I think the previous example might not have been. All right, let's try this one. Same idea. How do you solve for 3e to the t equals 5 plus 8e to the negative t? Looks tricky. I'll guide you. 3e to the t equals 5 plus, technically this is 8 over e to the t. I'm using rule number 7, index law number 7. Rule 7, a to the negative m is 1 on am. Okay, for those who forgot. And so I just switch that to the fraction, so it's 8 over et. Now, how do we solve this? Anyone have a clue? There's one step that I would do from here. What step should I be doing? Because it should change this problem back to the same problem as before. Ooh, you could, but then it makes a negative. I normally avoid negatives. At the moment, they're all positive, so positive, positive, positive. So I like to keep them positive, just to avoid any issues. But that's not wrong. It's not a wrong technique. But there's one thing that you can simplify your problem.
Take 5 to the other side.
Yep.
And then multiply both sides by 1 over e.
Very good. So that was the key part. That's right. So the key part is the fraction. So most students look at that and they get stumped. It's a VCAT question back in 2015. Most students don't like fractions. So first thing is get rid of it. Okay. One of the ways to get rid of it is do the opposite of divide e to the t times e to the t on both sides. So here, times this by e to the t, times this by e to the t. But remember there are 3 terms, so you have to also times that 5 by e to the t. What you end up with getting is e to the t cancels out. You get 5e to the t on the right-hand side, but what would you get on the left-hand side? So if I took 3e to the t times e to the t, what do you get? Index law number 1, same basis. What do you do to the powers? You add them. So what's t plus t? 2t. Or you can think of it as e to the t squared. True? Because you're timesing itself. So it should be e to the t squared. So another way of writing it is 3 e to the t squared. Can you see how that's turning into a quadratic problem like the one we did before? Okay, like the one we did before. E to the t times e to the t. It's just e to the t squared. But they both have e to the t on both sides. So if you want to make your life easier, you can do what I taught you before. I say let a random letter, so let's say A equals e to the t. Oh yeah, thank you. Plus the 8, I forgot the 8. I can replace this now. Put A, replace the e to the t, replace e to the t with a, and then suddenly your problem looks a bit easier if I rewrite it as another letter. So 3a squared equals 5a plus 8. That's just your chapter 3 stuff with quadratics. Now you bring everything across. Okay, so now you bring everything to one side. I would bring the right to the left because I like keeping my quadratics a positive number, not a negative number. That's my personal preference. It's up to you. But I would bring everything from the right to the left, so it becomes 3a squared minus 5a minus 8 is equal to 0. Now it's your job to factorize that. Factorize that using quadratics from chapter 3. Here we go. Who wants to have a go? That's the 2 brackets. Christina again. Minus 8? Yep. A plus 1. Let's see. 3a times a does give you 3a squared. 3a times 1 is 3. Just think it was 3a. And then this is a minus 8a. So negative 8a plus 3 does give you negative 5 that you want. And then finally negative 8 times 1 does give you negative 8. So it is correct. So now we factorize it. That was chapter 3. Let's solve it using null factor law. A could either equal negative 1 or a could equal to 8 on 3. But a was made up. A was e to the t. So this is actually saying e to the t equals 8 on 3. And this one is e to the t equals negative 1. Remember, this is year 12 exam question. Question 7b, 3 marks. Why is it 3 marks? Because one of them is a justification mark. Which one do you discard? The negative 1, but you have to tell them why. So here you'd say undefined since e to the t is greater than 0. So you're saying that the function e to the t always has to be a positive number, so that can't exist. So you're now left with e to the t is equal to 8 on 3. What are you trying to solve for? T. The question says find t. This is where you use log. So here 8 over 3 cannot be written as a base e, so you have to use logarithms now. How do I get t? You've got to get rid of exponential base e. So what would you do? Log base. Yeah, you could do log base anything you want. For me, I would do log base e, just because this is exam 1. You can't use a calculator. So exam 1, the easiest way to do it, I do log. And since that's a base e there, I do log base e. Whatever you do to one side, do to the other. Log e and e cancels out. And therefore t is equal to log base e of 8 on 3. Leave your answer there. In exam 1, you always leave your answers in exact form. You do not change to decimals, but you can't anyway because you don't have a CAS calculator in exam 1. That's 3 marks there. So method 1, that's mark 1, getting up to this step. Mark 2, which is that final line here, being able to get these 2 solutions. And method 3 is your justification. Okay, so mark number 3 is disregarding and getting a solution. Cool? Yeah, just leave it as log e of 8 and 3. All right, so that was a typical year 12 exam question there where you use both exponentials and logs. And your last one, I thought I'd just mention this. Be careful when you're doing logs with decimals, especially this one. So let's just do it very quickly. You got 0.7 to the power of x. Let's just make it equals to 0.3 for now. Inverse of exponential 0.7 to the power of x. What would you do? What's the inverse of 0.7 to the power of x? Log 0.7. Now this is where your textbooks might do it differently. They might do log 10 or log E. Just be careful when you're doing decimals. Log 0.7 of 0.7 will cancel out. You get x is equal to log 0.7 of 0.3. This one, a lot of students don't realize it yet because you guys haven't learned the graph. But there's a bit of logic here. 0.7 to the power of what equals 0.3, right? So if you just think about it as an exponential, 0.7 to the power of what to give you 0.7? What would it be? If I asked you, let's do a bit of logical thinking, 0.7 to the power of what gives you 0.7? X is 1. So this here, x has to be 1. Notice that's 0.7. That's much bigger than 0.3. So if I asked you 0.7 to the power of what gives you 0.3, you see at 1, x equals 1, but then say x equals 0. What's 0.7 to the power of 0? 1. So there's a bit something interesting here. When x is 1, it's 0.7. When x is 0, it's 1. So 0, 1, it's getting larger. But to get to 0.3, is the value going to be positive, negative, larger, or smaller? Negative? Let's have a look. So this is what I want you to think about. So when we say log 0.7, 0.3, can you see how it's getting larger? 0, 1, to get to, and this one's getting smaller. It's like 1, 0.7, 0.3. The reason why is if you think about the graph, remember I said anything between 0 and 1, the graph is decreasing. You're doing 0.7, the graph is actually doing this. Like that. Okay, so the larger the x value, the smaller the y values become. Okay, so when you do log 0.7 and 0.3, just be careful whether values are getting smaller or larger, and same thing whether it's getting negative or positive. Think about the exponential graph. Okay, but that's just something. So if we swapped it around, e.g. log 0.3 of 0.7. See, and what I want you to think about is 0.3 to the power of what gives you 0.7. Hopefully you see the difference between these two. See, if I asked you now, log 0.3 of 0.7, you see how it's getting smaller? Whereas this one was getting larger? It's that sort of concept. You have to think in terms of exponentials before the logarithms. Okay? Otherwise, I think I'll stop there. That's a lot of info for you to take. Hopefully what you've taken out from today is the algebra component. How did I go from here to x? That's what you're training in 13F. Okay? I'm going to leave it there. If you've got questions, let me know. But otherwise, that's it for today. I'm going to stop the video.